All right, in this video, we're going to be talking about section 11.3, which we're going to break into two parts. In this first part, we're going to be focusing on this concept of a tangent line to a curve. So let me set the scenario for you. We are going to be talking about what kind of would seem to be the impossible, which is we're going to try to find mainly what we're going to need is the slope of the curve. So what I'm trying to say very poorly is that if I identify a point, let's call this the point at XA. So this is the point A comma f of A. This is the function f of x. So we have this point here. And what I'm going to need in order to write the slope of the tangent line is I'm going to need to know what the slope is of the curve at this point, which is not something that is really easy, because I know to find the slope of a line, I need 2 points, and I'm only going to have 1 point. And so what we're going to be asking you to do is something that would seem on its surface to maybe be not possible. So here's what we're going to do. We're going to, on warm-up part A, we're going to find the slope of the secant line. And so first we need a secant line. If you remember, a secant back from the geometry days it was a line or line segment that intersected the curve, the circle, in 2 places. So instead of focusing on the tangent right now, I'm going to go ahead and just grab another point. I'm going to call this the point X. And so this is the point X comma f of X. And instead of worrying about a tangent line for now, let's worry about a secant line. And I'm probably not going to have the best line in the world here. It's not too bad. All right. So for warm-up A, and we'll go ahead and answer that maybe down here, we're going to find the slope of that line. And so we know that the slope would simply be, I'm going to call it slope, and I'm just going to kind of label secant underneath it. That would be y minus y. So we're going to do the f of x minus f of a over x minus a. Okay. So then what are we going to do to find the slope of the line that's tangent at this point? So of course, tangent is a line that would really just be touching the surface there and would look something like this. So on one hand, if we really want that slope, we could just use the slope of the secant line as an approximation. And I could say, well, we'll find the slope between these 2 points, which we did here, and we could just let that stand in for the slope. Clearly, that's not necessarily the best plan, because depending on how crazy the curve is, mine's a pretty smooth curve, pretty well gentle curves. But for all we know, there could be all kinds of ups and downs between these 2 points, making the approximation really, really, really bad. So what could we do? Well, we could, of course, move the point a little bit closer. So I could move the point to here. So then let's take away that, and let's just say this is at x instead. Then our secant line is the same equation, of course, but now it looks a little bit better. And then I could move it closer. I could not do the slope there, and I could move it closer. And then as I get closer, it seems to be a little bit better fit to the tangent line. And so if you think about this, what we could be doing is we could be like keeping track in a table. So we could identify an x, and then we could calculate the slope, right? So we're at this x, and we calculate, we get a slope. And then we get a little bit closer, and we calculate a slope. And we get closer, calculate the slope, right? And we keep doing this. That's going to be working great. But then when we get to the point itself, right? So let's say this point has got closer and closer and closer to A. As soon as I put in A, now I have no answer because, I would have A minus A in the denominator, which would mean, there's no answer to this question. And then if I looked at it from the other side, right, I picked, an A further away and looked at it getting closer to A. What it's going to tell me is hopefully that we see a pattern forming. And if this point that we've picked right here, as we get closer and closer to A, is microscopically close, then essentially we're going to have our answer about what the tangent line is. In other words, and I think everybody who might be listening to this video understands where this is going, part B, write an equation for the slope of the tangent line at x equals A. So for part B, we still have the same statement, f of x minus f of A over x minus A. But then what do I want to have happen? I don't want x to be a different point. I want x to be A, which we know to be impossible. So all I'm going to do is I'm going to say, let's look at the limit as x approaches A. And let's call this the slope of the tangent line. All right, hopefully that makes perfect sense. Not to be confused with finding the limit of the function. We know what the limit of the function is. Like, we know it's f of A. Like, that's where the graph is going. We want to look at what's going on with the slope at that point. And in order to do that, we just take our slope equation and, if all else fails, we can explore it numerically and kind of see what's going on. All right. Let's see if that gets us to where we need to be. Sorry about the extra gap there. All right. So looking at this, the slope of the tangent line to a graph, just what we just talked about. Notice this is the exact statement we just wrote. But I've introduced this notation. And the way we would say this is we would call it f prime of A is equal to, right? So f prime of A is how you would, if you were dictating it to me to write it down, you would say f prime of A. This has another name. This is called the derivative of f at x equals A, or at A. So this slope of a tangent line has another name. It's synonymous with this thing called the derivative. Okay, and then the notation to tell you to take the derivative is this. Okay, so let's go and take a look at example number 1. For f of x equals x squared, estimate f prime of 0. And what is f prime of 0? It's the derivative at 0. And what is a derivative? It is the slope of the tangent line at 0. So first thing we want to do is just estimate it. And, I know you all have a mental picture of this, but let's just get it on paper here. So here is x squared. And so the tangent line at 0 would appear to be this horizontal line right here. And we know that the slope of a horizontal line is 0, so I estimate that this should equal 0. All right, let's see if we can mathematically now show that that is the case. So we know, I'll go ahead and just write it right here, f prime of 0 equals, and let's since we haven't really done one of these yet, let's write it out. F prime of A, we know, is asking us to take the limit as x approaches A of the function f of x minus the value at A over x minus A. All right, so in our case, we're doing the derivative at 0. So we want the limit as x to approach 0 of f of x. Oops, not the symbol. Let's do the actual function. F of x is x squared minus f of A is us plugging in A for x squared and getting 0. So that's the y value, over x minus 0. All right, so back to our discussion about the indeterminate form. Obviously, if I just plug 0 in now, I get 0 over 0. And so we get no solution, or we get indeterminate. We don't know. But we obviously know that this just says the limit as x approaches 0 of x squared over x, which we know, of course, is the limit as x approaches 0 of x. And now I can actually take the limit. So now I can actually take the derivative. I'm going to plug 0 in, and now I get to drop the limit statement because I'm taking the limit. I plug in 0, and I get 0. So the limit is 0. The derivative is 0. All right, part B, let's see what the limit is at 1. And so we look over here at x is 1, and we can see we've got some slanted line. It's a positive slanted line. And so what's my estimate? I don't know because I didn't use graph paper, so it's hard to kind of get a good estimate. But I would say, probably somewhere in the neighborhood of 1 to 2, somewhere in there. Again, if I had bothered to take the time to do it on graph paper, I could probably come up with a better estimate. Now let's actually calculate it. All right. So this time I'm just going to start with the derivative at 1. I know tells me to take the limit as x approaches 1 of f of x, which is x squared still, minus f of 1, which is 1 squared, over x minus 1. So that gives me the limit as x approaches 1 of x squared minus 1 over x minus 1. All right. If anybody's instinct is to cancel out those negative 1s, you should probably stop this video now and go do something else. Obviously, we cannot cancel out anything unless they are factors, but good news, I can factor the top. It is the difference of two squares. And I know that cancels, giving me the limit as x approaches 1 of x plus 1. And now there's nothing stopping me from evaluating this just by plugging in the number. So now we actually can take the limit, and I get the derivative at 1. I'm just too lazy to write that the whole time. Plug in 1, and I get 2. What does that mean? That means the slope of the tangent line is 2. Okay. Negative 2. Based on our picture, again, we can see it in our head. If everything goes as planned, it should be steeper than the value that we had on the other side. It should be a negative number, and it should be something steeper than 2. So I'd expect something like maybe 4 or 6 or something like that, but definitely negative. So let's find out. The derivative at negative 2 is equal to the limit as x approaches negative 2 of the function minus the evaluated value at negative 2 here over x minus negative 2. The limit as x approaches negative 2, x squared minus 4 over x plus 2. We have the difference of two squares again. And when you take the derivative of the same function in different locations, it shouldn't be surprising that the method you end up using to get to the answer, how you simplify, would be more or less the same. So probably whatever value I plug in here, I'm going to end up getting a difference of two squares on the top, and I could follow the same pattern. If it was a different function, if it was x cubed or the square root of x or something like that, then obviously the simplification of this limit would look a lot different than for x squared, which we'll look at in a little bit. All right, limit as x approaches negative 2. My x plus 2's cancel. And now I can actually take the limit. And so I get f prime of negative 2 equals -4. Let's see if I can give myself some room here. My computer's bogging down. All right, and let's do, I think, one last one here. The derivative at a half. So same function. So we have the derivative at a half equals the limit as x approaches a half. By the way, the estimate here, we would expect it to be, if at 1 we were here, then at a half we're going to be a lower slope. So something closer to 0 than what we got at 1. So maybe the slope will be 1, maybe it'll be a half, something like that. All right, where was I? X squared minus 1/2 evaluated, right? So we want the y value at a half over x minus a half, which gives me the limit as x approaches a half of x squared minus a fourth over x minus a half. We can all hopefully see where this is going. I haven't addressed this yet, but I hope that you can see that when I'm writing limit over and over and over again, I get a little bit lazy with my symbol here, and my limit just kind of turns into more of a limit signature than an actual LIM. But hopefully, in context, you can tell what I'm doing. All right, x plus a half and x minus a half. Halves cancel. And I evaluate it at a half. And I can finally tell you the answer to that question. What is the slope at the tangent line? It is going to be a half plus a half, which is 1. All right. Pretty straightforward. Obviously, the more complicated the function, the harder it is going to be to calculate the actual limit. But the process in general is as we've shown. All right, one last example here. Find the equation of the tangent line to the function f of x equals the square root of x at x equals 9. So let's briefly take a look at what this is talking about. So we know the square root of x starts off very vertical and then transitions into something like this. And I know I have this point here at 0, 0. I know I'm at 1, 1. I know I'm at 2, 4. Obviously nowhere to scale. Let's maybe fix that. And then later on, I'm going to be over here at 9 and 3. So what I'm looking for is the slope to the tangent line of this function at 9. In order to do that, I need two things, just like we did way back in Algebra 1. We need a slope and we need a point. Well, we have the point. We have the point 9, 3. Didn't give us the 3, of course, but we can plug it in and find the y value. So I know the x f of x. I know the point here. And so the tangent line is going to be something that looks like this. So I'm imagining it's going to be a very low tangent, very, very small number, but positive. I'm imagining that our y-intercept will be somewhere in the 1 to 2 range here. And let's go ahead and start. So I need to find the derivative of the function, and I need to evaluate it at 9. So that means I'm going to take the limit as x approaches 9 of the function, square root of x, minus the square root of 9, right? At 9 is where we're doing this. So we already know that is 3. Over x minus 9. All right. So, okay, there's nothing to factor, so I can't do what I did last time. I suppose I should check. Can I plug in 9 and get a result? I get 0 over 0, so indeterminate. Here's a hint. It'll always be indeterminate. And so I need a new plan. And if we go back to what we did in the last section, um, when there's no obvious math to be done, you just have to be creative. And one of the creative things that we discussed was let's multiply by the conjugate of the top. So I'm going to multiply. And because of the nature of square roots, this is kind of when we want to try this trick. So the limit as x approaches 9 is now going to be what? X and x, that's going to just be x, and then minus 9 on top. On the bottom, I have x minus 9 times the square root of x plus 3. Because we're ultimately hoping things will cancel, we're not going to FOIL the bottom out because I want it factored. And so we can obviously see what happens. And I know it can be annoying, but every time you're doing the next line of work, make sure you're showing the appropriate level of work, or more than the appropriate for some of you. Until you take the limit, we need to write the word limit. All right. The x minus 9s will cancel, leaving me with 1 over the square root of x plus 3. Now I can actually plug in 9 and get the derivative. So the derivative at 9 is going to be 1 over 3 plus 3. It's going to be 1/6. Square root of 9 is 3. 3 plus 3 is 6. Yep. Okay. So that is our slope. So back to our problem. Now we know the slope is 1/6. So now it's just an algebra 1 problem. Y minus y1 is 3 equals our slope times x minus x1. Point slope is fine. I don't love point slope, mainly because most of our algebraic life we've gone beyond this, and so we're more accustomed to thinking about how accurate it is by thinking about the y-intercept, and I don't see the y-intercept in this equation. So I will go ahead and simplify it further just to satisfy my curiosity. 9 over 6 is 3/2, so I add 3 to both sides, and obviously I get 1/6 x, and I have negative 1.5 plus 3, so that's going to be positive 1.5. And that is pretty close to what I had estimated. So there is our slope of that tangent line. Okay, hopefully this all makes sense. This is the end of part 1. We'll see you on the next one for part 2.